Now we're going to apply the definitions and ideas of the previous lecture to the problems on graphs that we've been thinking about. So the first thing is to make this connection between totally unimodular matrices and bipartite graphs. The main result says the following. G is our undirected graph. And as usual, as we've defined in previous lectures, A is its unsigned, because we don't have a directed graph, incidence matrix. So it is the V by E incidence matrix, which means that it just encodes where the edges are. It's an entry of A is indexed by, the rows are indexed by the vertices, the columns are indexed by the edges. So A, V, comma, E is equal to 1 if E is incident to V, which I'll write in this way. That means if E is one of the edges, that's touching V, and 0 otherwise. So the theorem says that A is totally unimodular if and only if, so in fact it's an if and only if statement, G is bipartite. So we're going to prove one direction here. We're going to prove that, so the proof of one direction. We're going to show that if A is totally unimodular, oops, that's not what the direction I want to show. If G is bipartite, then A is totally unimodular. The equivalence is of interest, but this direction is actually the more pressing, we have more pressing need for this, because it basically tells us that the problems we defined for using our bipartite graph, namely the bipartite matching problem, is integral. So now we're going to use total unimodularity to basically reprove the fact that we have integrality of all extreme points of the bipartite matching polytope. If you recall, in our lectures on bipartite matching, we defined the LP relaxation, which we called Q, and certainly Q is a superset. It contains the convex hull of the incidence vectors of matchings, and then we showed directly that if it's an extreme point, it has to be integral. But now we're gonna we essentially get that again, but using this tool of total unimodularity. So we're going to we're going to show this by induction. So the proof is by induction on the size of the square submatrix. So in other words, what I'm saying is our task is to show that every square submatrix of A has determinant that's -1, 0, or 1. And so certainly for a 1 by 1 submatrix, well, we know that the elements of A are either 0 or 1. So this 1 by 1 case is immediate. And this is the base case for the induction. So now let's assume that, let's let A hat be a K by K submatrix of the incidence vector A, of the incidence matrix A. Now, and let's reason about it. So we want to show that that this has determinant 0, 0, +1, or -1. So what are the different possibilities? Let's also just briefly recall what does A look like. Now, if let me write a non-bipartite graph here and call this 1, 2, 3. This has edges E1, E2, E3. This would be a 3 by 3 matrix where I have the vertices V1, V2, V3 here, the edges E1, E2, E3. Vertex V1 touches E1 and E3, but not E2. Vertex, did I write this? Sorry, I meant this way. Vertex 2, V2 touches E1 and E3. E1 and E2, I'm sorry. And vertex 3 touches E2 and E3. Okay, so this is, again, just recalling what our matrix looks like. And now I'm saying let's take any square submatrix. So that's a hat here. This is what we've done. Now, what could happen if, I guess this is a too small example to see that, but you could imagine, in general, I have what does this look like? Any particular column just has 2 1s and a bunch of zeros. So if I were to take a submatrix, that was something like this. So this is my submatrix, then immediately I'm done. Why? Because I have a column that is all zeros. So that can't happen. Not that it can't happen. If it does happen, then the conclusion holds. So we're good. That's one of the cases where we're satisfied. So if so case 1, if any column of a hat is all zeros, then the determinant of a hat is equal to 0, and we're done with this case. What else could happen? Well, it's possible that any column, I guess I should just draw it out here. So what else is possible? If any column of a hat, remember, every column of the big matrix has 2 1s exactly. Right? That's what this picture shows. So it has 2 1s everywhere. Now, what would happen if I take a submatrix where there is some column that has a single 1? Well, then again, I'm in business, because all I need to do is compute the determinant by expansion by minors along that column, and that will be 0, a bunch of zeros, plus 1, or plus or minus 1 times the determinant of the submatrix. And now I can imply the inductive hypothesis. So if any column of a hat has a single 1, then by expansion by minors along that column and our inductive hypothesis, we know that the determinant of a hat will just be that plus or minus 1 times the determinant of the submatrix, which is assumed to be 1, minus 1, or 0. So, so we are also done. So we're only left with the case where all columns of a hat have 2 1s. It has to be that way. Now, we're going to use the one property that is in the theorem, namely G is bipartite, and we haven't had to use that yet. So what does G being bipartite mean? It means that I can partition my vertices into 2 groups where edges only go from one group into the other. In terms of the matrix, that says that I can partition my rows into 2 sets so that every column has a 1 in the first set and a 1 in the second set. So since G is bipartite, we can partition, I'm just writing what I said, we can partition rows into two groups so that each column of A hat, actually it's true for all of A, but each column of A hat has a 1 in the first group and a 1 in the second group. So what does that mean? That means my A hat looks like this, and I can partition, let me just, for my convenience, just assume the partition is into first half and second half. Obviously it doesn't have to be the case. And every column, the first column has a 1 somewhere on the top and a 1 somewhere in the bottom. And, similarly, this is what this looks like. What could the determinant of such a matrix be? It has to be 0, because the rows are not independent. I drew it to look rectangular, but remember that this is square. So let me note it since I didn't draw it suggestively. A hat is square, so the row rank equals a column rank. But the sum of the first batch of rows is just 1, 1, 1, 1, 1, because everything else is zeros. And so is the sum of the second batch. So in particular, A hat times the vector 1, 1, 1, minus 1, minus 1, minus 1 has got to be 0, is the all zeros vector. And that means that A hat is rank deficient, which means that the determinant of A hat is 0, and if the determinant of A hat is 0, it indeed belongs to 1 minus 1 or 0. And this concludes the proof of one direction. A more involved exercise is the converse, to show that if A is the incidence matrix of a graph, then if A is totally unimodular, then the graph has to be bipartite. So that's very, very interesting, and I'll leave that as an exercise, but it is involved, somewhat involved, or takes a few ideas. Okay, so now let's go back to, let's use this tool and go back to some of the to some of the results that we had shown and see what we can do with it. So let's revisit the min vertex cover problem. And what we had is we had written down two LPs. The max matching LP, which is maximize 1 transpose X. Remember this, the 1 is the all ones vector, and X for the matching problem, you're selecting edges. Subject to the fact that you do not select more than one edge for every that's incident to a particular node. So E incident to V, XE is less than or equal to 1. This is true for every node V. And also X is non-negative. And we also wrote down its dual. This was the min vertex cover LP. And this problem is to minimize the all ones vector. In this case, Y is we have a variable in the dual for every constraint in the primal. In other words, for every vertex. We already discussed this in more detail in the previous lecture. Subject to YV1 plus YV2 greater than 1 for every V1, V2 that's an edge, and Y greater than 0. So by our above results, we know that this matrix, so by the above, this matrix that defines those constraints is totally unimodular. And it's totally unimodular because G is assumed to be bipartite throughout everything that we've been talking about so far. Of course, we're gonna remove this and see that we need some thinking outside of what we've done. And now you can see why it was important in the previous lecture to show the link between primal and dual for our when in the presence of total unimodularity. So in particular, by that last result on the previous lecture, so by the Hoffman-Kruskal theorem from the previous lecture, the min vertex cover LP is also integral. And this gives us a simple proof. Well, simple, we've developed a lot of machinery, but basically this says that Konigs Theorem, which says that maximum matching, the size of the max matching, is equal to the size of the min vertex cover, follows from total unimodularity and from strong duality. So we're using more general machinery to reprove something that we had used reasoning that was very specific to this particular problem. And beyond that, it allows us now to generalize Konigs theorem to other things. And what other things? Well, we used a result that's actually more powerful than the way we used it. So if you recall, the result that we used said that if in the presence of total unimodularity, whatever the right-hand side is, as long as it's integral, gives an integral polytope, which means that if I'm maximizing any integral cost vector subject to a polytope that has only integral extreme points, first of all, the solution is going to be integral. And secondly, the value is going to be integral. And on the dual side, the constraints come from the objective function. So if the objective on the primal is integral, then the constraints on the dual are integral. And so again, we have integrality there. So the generalization basically comes from exactly what I said, but let's give some definitions. For B, an integral vector, a B matching is a generalization of the idea of a matching. And it is, rather than selecting edges, which we do to make a matching, we're allowed to put integer weights on edges. Another way to say that is that a B matching is an assignment. A B matching is an assignment that maps edges into non-negative integers, as opposed to just mapping them to 0, 1. So a selection problem is just mapping them to 0, 1. Where each vertex can be covered up to BV times. So in other words, the constraint that we had before, that this had to be less than 1, is replaced by the more general constraint that this is less than any integer BV, the vth component of B. And similarly, for any integer vector C, a C vertex cover is an assignment where now we don't have the requirement that every edge is covered by a vertex at least once, but rather it's covered at least C times. So it's an assignment Y, which maps vertices to non-negative integers, where now we need to have yv1 plus yv2 is not just bigger than 1, but whatever this value, whatever this value is. So the generalized Konigs theorem is, we've essentially just put words around what was obvious from the previous slide. So for any bipartite graph and any integral b and c, integral vectors of appropriate dimension, b is the length of the vertices and c is the length of the number of edges, the maximum C weighted B matching, so C attaches cost and the B matching is the constraints, is equal to the min B weighted C vertex cover. So again, this basically comes for free over Konigs theorem if we prove Konigs theorem using total unimodularity. We're going to stop here, and next time we're going to talk about total unimodularity and its connection to flow problems.